Good afternoon, ladies and gentlemen. Can you hear me? Apologies for a late start. I have had problems with my tablet, but it is okay now. Can everyone hear me well? Is all fine?
Yes, we can hear you.
Wonderful. Okay. So, today and next time, it will be myself. My name is Merkin, as you know, who will be providing the final two lectures of this term on a topic which I really hope will be interesting and challenging, and goes a little bit beyond the database technology. So we are going to talk about time series databases, or in more general terms, about time series processing in various areas such as computational finance, economics, modeling of real-life phenomena, and so on. And we're going to be a little bit mathematical today, not in connection with databases themselves, but more in connection with how we use time series and time series data, for which purpose, and what we do with them in general. So at this point, at the end of the course, I believe you have had already a very thorough understanding of the modern database technologies. So obviously, the bulk of current database solutions is still about relational databases. And the advent of relational databases was a major advantage in the development of database technologies that occurred in around 1970s. And since then, it has become a standard for almost all modern databases. Not necessarily, of course, there are many other solutions not following the relational paradigm, but still it was the advent of relational databases and the corresponding query languages which made the database technologies as we know them today. And yet, for a number of applications, as you already know, the classical relational database architecture is less than optimal. One area where it is indeed the case, and which requires significantly different and new technologies, is about storing and processing of time series. What are these time series? Time series are just any variable which is a function of real time or over timestamp. So time series is just a realization of a certain process. Let me call it xt, where t is time. Typically, this process is, it has many values. It could be just a number, it could be a record, and in that case, it would correspond to a row in a classical relational database schema. It could even be some unstructured data, which also depend on time. The most important thing is that the argument is a real time. And in that case, the main query operations or update operations, but mostly I would say query operations, which we need to perform with such databases are, first of all, searching the data according to the timestamps. So for example, there could be a typical query to select records in a given interval of time or corresponding to a given time instant. It is relatively uncommon but possible that you would need to perform some update operations on these databases. So once this real-time data stored, they may or may not need to be updated. In general, updates are relatively uncommon. So the typical operations which we need to perform on them is, first of all, an efficient insert, and then efficient queries. Update, as I say, may or may not be necessary, or at least the time series databases are not to be optimized for efficient update. What kind of data we are going to talk about, and how much data can we actually imagine in such case? In some extreme situations, the amount of data we need to deal with can be absolutely enormous. The time series databases primarily originate from the need of the computational finance. I believe that you may not have any background knowledge of computational finance and how it works, so I will provide you with some introduction into this subject. But you should probably know that there are some financial instruments and asset classes which are traded at financial exchanges or by some other means. So, for example, everyone have heard about such financial assets. Let's classify them. So what is the most well-known financial asset? The most well-known financial asset is called equities, also known as stocks or shares. And there are very well-known international as well as Russian financial exchanges where these equities, also known as stocks or shares, are traded. So the best well-known financial exchanges, you have probably heard about them, are like New York Stock Exchange, abbreviated to NYSE, NASDAQ, where technology company stocks are primarily traded. A relatively new but very important, again, American financial exchange, which is called BATS. So those are in the US. Some European exchanges, for example, the London Stock Exchange, LSE, don't confuse it with the London School of Economics, same abbreviation, LSE. Some continental exchanges, for example, Deutsche Börse, German exchange, the Moscow exchange, which is called MOEX, which also has an equity section, apart from others. Obviously, exchanges in the Asia Pacific region, there are many of them, and so on. In general, equities traded at the exchange have a huge total value. As a rule of thumb, I can tell you that the total valuation of international public equities, by public equities, we precisely mean equities which are traded at financial exchanges. Total valuation is roughly equivalent to the annual GDP, gross domestic product, of all countries in the world. World annual GDP, roughly, which is roughly equal to, it's impossible to give any precise values because obviously the world equities lost about 15% of their value, if not more, from the beginning of this year, unfortunately, due to this coronavirus outbreak, and the value is changing daily. But we are talking about a value which is under 100 trillion rather than billion dollars. 100 trillion. That's a rough value of the world equities. And this is the best well-known tradable asset. So when we think about an exchange, about trading, then probably the first thing you can think about is really equity trading. In the US, you know that equities are organized into tiers. There are highly capitalized, the most important ones, which are grouped into the Dow Jones Industrial Average. You remember? Industrial Average 100, which is 100 most important US stocks. There is a larger index, S&P Standard & Poor's 500, which contains 500 still very important US stocks, and this relationship between them is by inclusion, so S&P 500 does include Dow Jones 100. There are also, and we can think of them as being tier 1 US equities. There are also less highly capitalized equities, making indices such that Russell 2000 and Russell 3000. So at the bottom, there are 3,000 US equities being traded. In the Moscow exchange, there are hundreds of Russian equities being traded, but there are 50 most important of them, and those 50 most important equities make the index, so-called. The index is just the average price of those equities, the index of the Moscow exchange. You can imagine that probably by far the most important equities are Gazprom, Lukoil, Rosneft, and others. So primarily they are in hydrocarbon energy sector. Not only Aeroflot is on this list. Sberbank, by the way, is one of financial sector Russian equities. But obviously the depth of the Russian equity market is very much limited. So what we compared to the US market, let's say the equivalent of the Russian 50 top equities would probably be S&P 500 in the United States, or possibly even larger. So we have much more depth and much more value in the US equities, as well as international equities traded at European and Far Eastern exchanges. And then you can imagine that there are really millions and millions of trades being done every day. And the information on these trades is important. It is important from the point of view of economic analysis, from the point of view of making predictions for stock prices and buying and selling equities based on those predictions. So all those trades are actually to be somehow stored precisely in time series databases, and this corresponds to a very large volume of information. But the story doesn't stop there. Equities by themselves, you can roughly estimate how many trades are being done per day. We would say that at a given exchange, the average interval between the trades is less than 1 millisecond, significantly less than 1 millisecond, which means that if trading is not 24-hour, it starts at 9:30 and finishes at 4:30 p.m. typically for the United States exchanges. Therefore, we're talking about 7 hours. But even 7 hours are very roughly, we would say, 20k seconds, in fact more. But there are different liquidity periods. And if the average period between the trades is less than 1 millisecond, then we would have 20 million trades. In fact, much more actually than that per day. But that is for just one exchange, and I would say probably just one liquid instrument. If you multiply this 20 million by the average number of liquid instruments, which correspond to that amount of trading, then you would need to multiply it by at least 100, and therefore you end up in 2 billion trades a day, which is already a sizable, quite a sizable information. Apart from the trade data, there are other very important data items to be recorded from the financial markets. So first of all, even let's analyze a very simple thing. What is a trade, and what kind of information do we store about a trade? So first of all, we will typically have a timestamp, obviously, and modern exchanges provide timestamps at least with a microsecond resolution, maybe nanosecond. Long past are the times when a millisecond resolution was enough. As we can now see, there are many trades which can occur within a single millisecond interval, and that's why typically modern exchanges provide microsecond level timestamps, which is interesting from the time keeping point of view, because in order to provide a microsecond timestamp which is meaningful for subscribers of this information, the exchange clock and the subscriber clock need to be synchronized to a microsecond level. If you think about the general protocols of time management, timekeeping over the internet, for example, the classical NTP protocol, you know that NTP is only capable of a millisecond accuracy. So the exchange can still provide you with microsecond resolution, but this wouldn't tell you much, because it would use its own internal clock, not synchronized with your clock over the recipient of this information. So suppose that you connected to the exchange and you receive this trading information. Without having your clock synchronized with the exchange at the microsecond level, you wouldn't be able to tell, for example, the trip time for the information from the exchange to you. And this trip time is of critical importance for development of automated quantitative trading strategies, computer-driven, which are in particular popular in the equity markets. So NTP is a thing of the past, and you have probably heard about the new protocol, which is called PTP, which is using specialist hardware, typically GPS clocks. And with GPS clocks, you really should be able to achieve the microsecond resolution level. So the timestamp will be 15. Then obviously the symbol. The symbol is precisely the name, the short name, a few letters of the financial asset being traded. Some symbols are very easily recognizable. So for you, just what does symbol F stand for? Anyone can guess? In the American exchanges, of course. Ford. Obviously GM, you understand that this is General Motors. Okay, this symbol you no doubt know. What is this? Any idea? Apple, of course. And so on. So a symbol is typically a short few letters designation of the equity being traded. Apart from the symbol, there is typically a standard instrument ID, which would be a number. So either a symbol or instrument ID can be recorded in this case. Now, when a trade happened, there is an important characteristic of the trade, which is, well, first of all, there is a size, which simply means how many shares. How many shares traded in this case. Or sometimes you cannot trade a single share. It depends on the exchange rules. You can only trade multiples of, let's say, 10, 100, and so on shares, which are called lots. A lot is a certain package, a multiple of a given number of shares. So alternatively, it could be a number of lots. Price, at which I am using PX as a standard abbreviation of price, but you know that it means price. At which this trade has occurred. It looks like that is probably all about the trade information, but it is not all. In order to explain yet another very important characteristic, I will need to tell you a little bit more about the mechanics of financial trading. And you have probably heard the notion of the order book. That's about how trading is implemented at the majority of exchanges. So basically what happens is that when you or any other exchange participant want to sell or buy a share, then you submit a request to the exchange saying that I would like to buy or I would like to sell at a particular price. Your requests for buy or sell at a particular price are put at the exchange data structure, which is precisely called order book, but they are not immediately executed. So your willingness to buy or sell doesn't necessarily mean that there is a counterparty who would like to, if you want to buy, for example, to sell you at that price which you specify, or if you would like to sell, then there is a buyer at that price. More likely than otherwise, you submit your requests or orders to the exchange, but they are not immediately filled. Instead, they are put into this order book data structure, waiting for the better time when they really get executed or traded or filled. These terms are generally equivalent. So what happens? Suppose that there is a certain equity X, and you would like to, for example, buy this X at, let's say, the price of $100. So you submit a request for a certain quantity of your shares, for example, 2, at the price of $100. But, and you would like to buy, okay, buy at 100. But there are no sellers at the moment who would like to sell you at 100. There are only sellers who want to sell, maybe there is one who wants to sell at only $102 and not 2 shares, but only 1. There is another one who agrees to sell even at a higher price at $103, and then there are 3 possibly shares available, and so on and so on. So it might even be that you would like to buy for $100, but there is someone who agrees to buy at $101 and would like to buy as many as 5 shares, for example, at that price. So here there are sellers who want to sell, and this is also called the ask side of the order book. Here there are buyers who would like to buy, and this is also called the bid side of the order book. And you see that at each particular moment, the lowest price at which the sellers agree to sell is higher, strictly higher, than the highest price at which the buyers agree to buy. So there is a gap between them. And this gap is called bid-ask spread. And nothing happens. You placed your order here. You only want to buy at 100, but no one would sell you at 100. But sooner or later, the situation changes. If it were like that and the situation is stationary for ages, then there are only orders that they change, but these orders are not filled. As you know, in a Russian proverb, there are 2 RMs standing on a narrow bridge, and no one can see the path to the other. Nothing happens. No trades occur. Fortunately, at some point, there is someone who says, okay, I need to buy urgently. I am no longer in a position to wait indefinitely until the trade happens. Okay, I wanted to buy at 100, but I see it can't happen right now. But I want to buy for some reason. Maybe I have made a prediction that the price will go up. And that's why I want to buy now in order to benefit from this price run up. So what this owner of our order for $100 would do in that case, they would raise the price to match at least the lowest sell price, the lowest ask. In this case, this is not exactly sufficient. Even if you raise your price from $100 to 102, you can only buy 1 share at the price of 102 because only 1 is available, but you would like to buy 2. Therefore, what you actually need to do is to raise your price to $103. And in that case, you will first so-called lift or match this order at the price 102, buying 1 unit, 1 share, and then out of the 3, you would buy 1, and therefore your order is going to be filled. So after that, the order book would have a new structure. There are still 5 orders at the bid side at the price 101, because the owner of these shares did not raise the price and is still staying there. The price level of 102 is completely taken. We have taken it. At 103, there is now only 2 shares remaining, and so on. So that happens. And this situation, when someone wants to buy or sell immediately, and for buying raises the price to match the price of the sellers, or if someone wants to sell immediately, they lower the price to match the highest price of the buyers. This situation is called aggression. And that's why when we record the trade information, it is not just sufficient to know at which price the trade was made. It is also important to say who was the aggressor in this case. So either the buy side or the sell side was the aggressor. If the buy side is the aggressor, then we call it a lifted price, because it was originally a lower one, but then it was lifted or immediately set from the very beginning to match the price of the sell side. Or if the seller was the aggressor, we call it a hit. So aggressor side, buy or sell. So altogether, this is information about our trade. And as we say, there could be hundreds of millions or maybe even billions trades which occur every day. But it is also very important to record not only trades, but precisely snapshots of the order book. Why? There could be many order book updates before a single trade occurs. So for example, someone could add extra order at the price 101, and it used to be 5, now there are 6 here. There is no trade yet, but it is a new event, which may that mean that someone is increasing their potential order to buy. And we can imagine that, for example, when the orders are mounting up on the buy side, and the orders are not, for example, that quickly mounting up on the sell side, then this probably tells us about something. Because if there are too many orders here at the buy side, and they are not executed, and there are fewer counterparties actually, suppose that there are now 5, 6, 10, 20, and so on orders still sitting and waiting at 101, this probably means that the probability is increasing, the likelihood is increasing, let me say, that the owners of these orders will soon stop waiting for someone coming from the sell side and executing them at the price 101. They will really go aggressively and aggressively buy at the sell side. This is a so-called order book imbalance. When a significant imbalance occurs on one side, for example, on the bid side, this is an indicator that probably aggressive lifts will come, and as a result, the price will eventually go up. Here, for example, in the original setup as we had, there was best buy price at 101, best sell price at 102, and we can say that there was a mid price, just a theoretical mid, which was obviously 101.5. After we lifted just two orders on the sell side, it is now 101 to 103, and therefore the mid is now, as you can easily see, at exactly 102. So aggressive buying typically results in the price going up. Aggressive selling results in the price going down. That's why if we see that there are already a lot of, for example, buyers position themselves to buy, then it is only a matter of time, and probably a very short time, that they are going to aggressively buy and moving the price up. Therefore, for running various analytical algorithms on our order book, it is very important to record not only trades, but record the order book updates as well. And in that case, the amount of data which we need to record in our time series databases becomes truly enormous. Okay, for a trade, let's roughly estimate how much data we need to record. Okay, so time series with a microsecond resolution is typically an 8-byte timestamp. Okay, a symbol is for most exchanges or a numerical ID would also fit in 8 or maybe even 4 bytes if you really want, but to make it consistent across multiple exchanges, let's say it is also 8. Size as a number of shares, interestingly enough, and it is a common pitfall. Some people would say that it is okay to use a 4-byte integer, but I have really seen in my practice the situations when it caused errors. That, for example, there are very cheap, just penny level shares and purchased in such quantities that a 32-bit integer was not enough, and therefore it is strongly recommended to use also 8 bytes to specify the quantity or the size of the trade. Price. It is a very interesting question actually how we represent the price. The price can be represented in as a floating point number, but then there are problems with exact comparison and price step and so on. So typically, the exchanges for all instruments traded at the exchanges, they do have a fixed price step. So in the example which we considered here, the price step is equal to $1, or it could be smaller. So the price could be probably a 4-byte quantity expressed in the number of price steps. Together with alignment and with the aggressive side buy or sell, which is for a Boolean 1 byte, but let's say for alignment, we'll say 4 bytes as well, we'll have 8 altogether here. And therefore we have 1, 2, 3, 4 fields, all right, therefore of 8 bytes, therefore it is 32 bytes per trade. But if you have all in all in your exchange just roughly estimating 1 billion trades per day, for simplicity, right? 1 billion trades per day, then it is already 32 gigabyte of trading data of only trades per day. At less liquid exchanges, for example, like Moscow exchange, it wouldn't be 32 gigabytes, it would be, let's say, 1 or 2 gigabytes a day. But we know that we are now in dozens, or maybe in the most liquid cases, it would be up to 100 gigabyte only of trade data per day. But we also need to store the order books. And then the situation is much more severe with the order books. First of all, order book updates, which do not yet result in trades, are much more common than trades. On average, I would say, any guess? Let's play a quiz. What do you think? How many order book updates, just passive orders not yet resulted in trades, being placed at the exchange? How many order book updates per one trade would typically happen? Just by the order of magnitude. What do you think? Please turn on your microphones and tell me what do you think about it. Hundreds. Almost correct. I would say not hundreds, but dozens definitely. Let's say 30 to 100. Yes. Order book updates per trade. And now you need to store either the incremental update, but the incremental update would also need to be specified. Okay, so what is the order book update? Update in the simplest case would mean that at a given, so first of all, at a given time with a timestamp, at a given price level, there is a size delta. Okay. This is 8 bytes. Price and delta size, if you do it economically, you can fit all together again into 8 bytes. So 16 altogether, but if, for example, we have on average, let's say 50 order book updates per trade, and we'd say the trades are about 1 billion, actually. Therefore, there are 50 billion order book updates per day, roughly, possibly more. And multiplying this by 16, we are already in 800 billion, or let's say 1 terabyte of updates data per day. Okay, updates data per day. And that is if we store this very, okay, by the way, this is not exactly the case because we may need some extra information. So first of all, there is a symbol here, okay, which is 8 more bytes. And then we may or may not encode any extra information, for example, which side of the order book buy or sell. So in this case, we would say price is 4, delta size is 4, side is, although side can probably be inferred from the price, but it is better to store this separately. And therefore, we have already 16 plus 12. Therefore, very roughly, we would say there are 30 bytes instead of 16. So we have 30 here, and therefore we are in 2.4 terabytes a day, something like this, on order book updates. Furthermore, this information is, if we only store these incremental updates, is a little bit inconvenient. It is okay for storing, but you would probably like to store the entire order book snapshots up to a certain depth, because this incremental information is very much inconvenient to work with. So if we store the order book snapshots, so really, for example, we consider our order book and we store, let's say, in the simplest case, maybe 5, 10, these are typical values, 20 or 50 levels at each side. Okay, maybe for simplicity 10 is okay, but in most serious applications it is not. Then we would need to basically multiply the whole information by 20 or so. And we are already in about 50 terabytes of data per day. By the way, there was a question in our chat. What is the terabyte price in the example we have considered? Good question. So I will explain this once again. When we were taking 2 of our orders and matching orders at the opposite side. So first of all, there will be 2 trades here, not 1. Each individual match at a particular price level, there will result in 1 trade record. So there will be 1 trade at the price of 102 at the price 102 for 1 share, and another trade at the price 103 for 1 share as well. So 2 trade records. Sometimes the trade records are aggregated if they resulted from the same aggression, because it was actually same aggressive order being executed and matching 2 previously installed passive orders. And in that case, you would get just 1 aggregated trade for the average price, which is in this case obviously 102.5. But this is undesirable. It is much more informative for subsequent analysis to store individual trades as they happen. This is not even all. Now I will tell you about the most horrible situation which may occur from the database design point of view. In the United States, there is a national legislation which is providing the mechanism which is called NBBO, which is National Best Bid and Offer. Offer is another term for ask. So bid is the bid or buy price. Offer is ask or sell. What does it mean? Why national? Why best? Suppose that you want to buy Ford shares, for example, 100. The shares are traded at several exchanges, so definitely they are traded at NYSE, but they also traded at BATS, and maybe at some other exchanges as well. So this mechanism, which is mandated by the US legislation, it is a law. It allows you, the exchange client or the investor or a trader, to simplify your life. You don't need to connect to both actually NYSE and BATS and compare in real time the update streams coming from both, and then checking where, for example, the current sell price would be lower, so then you buy it aggressively at that exchange. What you can do is to connect to only one of the exchanges, and they're all connected between each other into this NBBO network, and you can submit an order for NBBO execution through gateways into each and every of these exchanges. And then if another exchange has, for example, a cheaper price for you, then your order will be automatically routed to another exchange. You are currently at NYSE, but through this NBBO mechanism, the exchange side, this infrastructure, automatically recognizes that the price will be lower at BATS, and your aggressive buy order is transmitted to BATS instead of NYSE for immediate execution at a better price. This is a mechanism which allows the general public, the investors, the traders, to trade at more efficient markets, let me say so. So it effectively eliminates, unless you really make very, very, very sophisticated mechanisms working faster than the generic NBBO, the price discrepancies, or we also call it arbitrage, between the different exchanges. So this is good. This is good for traders. It is very difficult to implement, but it is implemented. And instead of connecting to a particular exchange, you can subscribe to an NBBO national unified feed and receive updates across multiple exchanges at the same time. If, for example, you don't need it for optimal execution, your order will be routed anyway. But if you want to store those prices for statistical analysis, then you can subscribe to NBBO, and you will get in one feed the prices coming from multiple exchanges. But the story doesn't stop here. Apart from equities, there is such a thing as equity options. Okay. Equity options. You have probably heard about options as financial instruments. I will not give you very much detail about how options work, but still will provide some example. Suppose that for our X share, which we considered previously, the current price is, let's say, now we have t equal to 0. The current price x0 is $100. Again, when we say the current price is, you immediately should tell me stop please explain what the current price actually means. There is no such a thing as the current price. We can say that there are at least two and possibly more definitions of the current price. There is a current bid, best bid price. Yes, that's the current price. There is a current best ask price, which could also be termed the current price. There is probably a better measure, which is the current midpoint price, yet another one. Or there could be the price of the most recent rate. And as we discussed, the most recent rate would occur either by lifting the price on the bid side, on the ask side, or hitting the price on the bid side. And therefore, it would typically oscillate because trades are coming in both directions. The most recent price would oscillate around the mid price, but the mid price is slowly moving as well. So for example, if there is an uptrend, so that's your mid price, but the actual trades would occur sometimes below, sometimes above, sometimes below, sometimes above, and so on in this zigzagging way around the mid price. Therefore, we really, when we say that the current price, we need to be careful explaining what exactly it is. So for the moment, for the sake of the argument, I would say the current price is the midpoint. At least the midpoint would evolve much more steadily without this zigzagging line compared to the last trade price. Okay, suppose that with our definition, it is the midpoint. Okay, now what the option is? It is a contract which is given by one party to another party. It is a financial contract. An equity is also a financial contract. But the option is a much more interesting kind of contract, which says, okay, it is now time t equal to 0. The contract specifies, I am talking in particular about a so-called European call option. There are many types of options. European call option. There are European options in the United States as well, although there are also options of American type, a little bit more complex. So let's focus on the European one. The European call option says, okay, there is some fixed time instant, T capital, which is called expiration time. Typically, there are options which expire every week, for example, in midweek, or every month, or every quarter. So, for example, today is Monday, and we would say there is an option expiring, a monthly option expiring in mid-May. It is Wednesday, mid-May. I don't remember which calendar date it will be, but let's say, for the sake of the argument, let's say it is 15th of May. And the option contract is effectively a lottery ticket. It has another parameter in it apart from T capital, which will denote by K, and it is a strike. The owner of this lottery ticket or option will receive a win at that time when the lottery is played at T capital equal to the price of our equity at that time, XT capital. And obviously from now, from the current perspective at T equal to 0, we don't know that price. For us, it is a random variable at the moment. at t equal to 0. It will become deterministic or fixed only at time t capital. Before that, we can only view it as a random variable with a certain distribution. And the win or payoff, which the option holder or lottery ticket holder will receive, is equal to xt minus k, provided, of course, that xt is greater than k. Or 0 if xt is less than or equal to k. Or we can say, as an overall formula, it is a maximum of xt minus k and 0. Okay? In order to be eligible for this lottery playing, you may win something, you know. You will not lose. In the worst case, you simply do not receive any payoff, but you may win. Obviously, no one will give you such a lottery ticket for free. If you buy this lottery ticket from someone who is called the option underwriter, they will require an upfront payment, precisely like you pay for the lottery. And this upfront payment is called at time t equal to 0, when you need to pay. You buy the lottery ticket now, and the lottery is played at time t capital. It is called option price. So the question is, how much are you prepared to pay for the lottery ticket, which may or may not give you such a win at a later time? Or other way around, how much the underwriter of this option, or in other terms of the lottery, is going to charge you in order to be able to eventually have enough money to pay the payoff if really this win occurs. So this option price is obviously a function I will denote it by C at time t. C for call, but it doesn't need to be a European call option. There are many other possibilities. It is a function of, first of all, of the current price of your equity, your stock. Obviously, it depends on the option strike, the time remaining to expiration. If, for example, your current price is already significantly greater than the strike, and the time remaining to expiration, t capital minus t current, is very small, then with a very high probability the option will win. So you'll probably imagine that the price should be higher than in the situations when xt is less than k and or significant time remains to option expiration. Interestingly enough, without going into detailed theory, it would depend on two other important factors. The risk-free interest rate, precisely, you know, that interest rate, which, for example, in Russia, the Russian central bank is setting, and which was set at 5.5 percentage points yesterday, or which is nearly zero currently in the United States. And it will also depend on a very difficult to measure and I would say enigmatic parameter, which is the volatility of the market, or precisely of this XT stock. Volatility, roughly speaking, is, I will not give you the exact definition in this case, but it is a kind of standard deviation, which is familiar to you from your probability and statistics course, which I believe you have just started this year. And this is the risk-free interest rate. And For each equity, there could be multiple options created on this equity. These lottery tickets options are a very, very popular thing in financial engineering. It is not just a lottery, it is a very major and very significant financial instrument being used by all market participants, from private individuals to large corporations, banks, hedge funds, and so on. So imagine that for each equity, I would say liquid equity. Okay, there are 500 liquid equities from S&P 500 list. For each liquid equity, there would be, let's say, 10 options at least for each. What does it mean, 10 options? With different strikes and different expirations. Now, the option price changes every time when the underlying price changes, and if the equity price changes. But we said that the equity prices change because we, in our definition, we said it is a midpoint price. They change not only when the trade occurs, but also when a midpoint price changes due to, for example, just orders being placed or deleted, removed without trading. So there are enormous number of events when the option price can change, and there are multiple options per equity. So altogether, we end up, and these options are traded at multiple exchanges as well. So for example, BATS is one of them, but there are other option exchanges in the United States. So when this NBBO feed is applied not only to equities themselves, but for options, you immediately get a very remarkable figure of about 1 million updates per second. And therefore, if it is 1 million per second, then okay, they are not equivalently distributed over the time of day, but if there are, let's say, 20 or 30,000 seconds of trading time, then we're talking about therefore 20 or 30 billion updates per day. And if each update is okay, as small as, okay, for options, we need extra information with option designation, exchange, and so on. So let's say realistically, we can probably say 100 bytes per update, which we need to memorize in this case. A billion updates, 100 bytes per update. Therefore, we have precisely 3,000 updates and 3,000 bytes, and therefore we again end up with things like in a terabyte region per day. Okay, so in this case it is going to be 3,000 gigabytes per day, therefore 3 terabytes of data per day, and that is on top of the snapshots for equities, which in a compact representation, it is about a few terabytes. In a sparse representation, it can be hundreds of, dozens of terabytes. So all in all, we are probably talking about at least several dozens of terabytes of updates per day from all those instruments. Okay, so as a very, very, very minimum, it is 10 terabytes, but possibly more. But that is again not all. We're only talking about equities. Apart from equities, there are other assets, other financial assets, other financial asset classes. So for example, the most liquid one in terms of the number of trades is FX or Forex or foreign exchange. To give you an example, just a single FX trading firm, not the market as a whole, but a single FX trading firm, there is a company which is called, let's say, XTX, which is the market leader. A few years ago, they had a trading volume of USD 75 billion per day. When we add up other exchanges, proprietary exchanges, many other networks of which FX trading happens, then we are in several hundred billions per day. Even, well, okay, if we take the most liquid ones, I would say, let's say we're in 200 billions per day. Okay, now the average size of one trade in FX. So for example, when you sell euros by dollars, you trade your USD or USD ruble and so on. The typical trade in FX is probably under 1 million. So in that case, a typical trade size, let's say typical trade size is 500K. Is 0.5 million. If it is 0.5 million in general, okay, and we have 20 billion, therefore we have, sorry, 200 billion, therefore we have 200,000 millions divided by 0.5, okay, so all in all, it is about 400K FX trades per day. As you see, it is interesting. It is a smaller number in terms of trades compared to equities, but the volume, the size of each trade can be very, very significant. So in terms of monetary turnover, FX exceeds equities in daily trading. So total capitalization is high for equities. Total daily turnover in monetary terms is high for FX. And for FX, again, we have options. We have other FX products. There are other asset classes such as, let's say, bonds, other interest rate products, so financial instruments whose value is primarily based on the interest rates. So altogether, if you are a trading firm, and this is a completely realistic scenario, a completely normal paradigm, we would end up with, as our computations have shown, about 100 terabytes of data per day. If you really subscribe to all those markets and you record this data. Probably it is excessive. It is unlikely that as a trading company you would be interested in all this data across all asset classes. Okay, I can divide it by maybe 10, maybe more than 10, but let's say up to 10 terabytes a day, certainly. That's about the amount of data we need to deal with. And the data are typically organized in time series, so that you need, as we started our discussion with, to implement, first of all, efficient insert, or more precisely, efficient append of our data simply for memorizing them in financial database, efficient query, and then some efficient ways of processing the data. So let us have a discussion from what you have already known. Suppose that we don't have any specific time series databases. Which database solution you would use if you need to store up to 10 terabyte of data per day? Okay, even not 10. Suppose that 1 terabyte of data per day. But still, 1 terabyte per day is a very minimum which you need to process. Primarily, I'm asking about just storing this, so providing efficient append of your data to the database. The data of the types we have discussed so far. So which database solutions you are already aware of, and you have been already programming such database systems. So which system would you recommend for storing in the first place for efficient append of up to 1 terabyte of data per day? You can buy a 10 terabyte disk. It's not that much important, that much expensive. Okay, so a distributed one, like Hadoop, might be, but my question is, how is it optimized? Is Hadoop optimized for massive append? It is definitely optimized for, let's say, distributed processing. You can run algorithms on top of that. But from just a very simple append operation point of view, would Hadoop be optimal? The answer is we don't know. We really need to measure the performance. But in general, I would say that it may or may not be. For simply storing or appending data, the very, very, very simplistic solutions are the best. So if we're only talking about don't be too complex when we consider solutions like that. You know, when we only need to store the data, a very simplistic solutions like, let's say, a file or a memory mapped file might be okay. Redis, possibly. I would say for simply storing the data, a very carefully crafted MySQL is quite okay. So for storing, it is not really a big problem. In any case, the fewer processing operations you do, in this case, you only need to manage the overflow, basically, to switch to another drive, to another local host, and so on, if you simply store the data. All solutions you mentioned are probably adequate, but in order to select the right one, we really need to run stress tests and consider the performance. My first solution of choice, however simplistic it would look like, would not be Hadoop or Redis or any special time series databases we are going to talk about and examine them in detail next time. But a very simple file-based output may do in this case. But when it comes to processing of that data, the situation is now completely different. A very simple, what kind of processing could we do with, let's say, price information recorded in our time series database? Can you suggest any simple operation which we will do in that case? Meaningful. So what could we do? What could we want to do with this data? Okay, stored. What then? Different types of statistics, for example, aggregation. Yes. A very typical example is applying digital signal processing filters to our data in order to be able to detect some trends. Are you familiar with, have you had a course maybe already of digital signal processing, DSP? Or not yet? Not yet. Never mind, we'll introduce a very simple concept of that right now. Suppose that this is time and we recorded a very highly oscillating price of a financial asset, okay? Something like this. But you can probably see that, so this is our XT, which is, let's say, again, midpoint price. Midpoint price. That in addition to high frequency oscillations, there are some longer term periods corresponding to our price curve. So generally speaking, this price curve can somehow be made more smooth. Okay, so what we do in this case, we are, okay, I'm doing this by hand, we are constructing some kind of trend detection. Why is it important? Because obviously the trend changes its direction from uptrend to downtrend, or let's say changes its derivative only infrequently in extremum points, which are very few in the graph we have identified, whereas the price itself changes, has multiple innumerable number of extremal points, and actually from the mathematical point of view, the price curve itself is not even considered to be differentiable. It is a continuous but not a smooth function. From mathematical analysis, you probably remember that continuity doesn't imply smoothness or differentiability. And that's precisely an example. A path of our curve, of our price curve, is an example of a continuous but not differentiable function. So making predictions about that function is relatively difficult. But making predictions about a smoothened curve, which is precisely the trend, is much easier. So for example, we know that from this point on, we now have an uptrend. We don't know where it finishes, But at the moment, we see that there is an uptrend, and we can possibly, by modeling it using some, let's say, piecewise quadratic or otherwise polynomial or any other technique, we can predict that at the moment there is no sign of trend derivative vanishing, and we can, for example, buy our asset and write on this trend in the hope that the price will continue to, on average, increase. So which techniques can we use in order to detect those trends? In this case, trend detection is equivalent to applying a filter which smoothes our curve. The simplest and by far the most commonly used filter is called the EMA, which is exponential moving average. How it works? You have time series of your xt already discretized. By the way, they do not necessarily correspond to equally distant time points. You store all the updates the time when they occur. So x ti at some ti times. That's what you have for I from 1 to some big N. Then you define this EMA in the following way. You would say for different I, you would initially start E0, let's say it is the initial value of our process, x t0. And then at each subsequent point I, you would have the following update formula. EI would be equal to the previous value which you took with some weight, let's say alpha times EI minus 1, plus alpha is called weight, obviously, which is in between 0 and 1, plus 1 minus alpha times the new update xti. And that is a very interesting thing, actually. You do indeed achieve a smoothing effect this way. Obviously, if alpha is close to 1, then the weight of previously computed EMA here is high, and the weight of new updates is small. So alpha about 1 means that you have basically a very high effect of smoothing, but as a result, you really get a relatively smooth curve, but as a result, it has a very, very, very significant lag, because the new updates come with a very small coefficient, 1 minus alpha, which is close to 0, and in that case, they do not play any significant role. So, for example, if your price curve is like this, first you oscillate around one value, and then there is a jump, and you start oscillating around another one, then by using alpha with a value close to 1, you would really get a very, very smooth curve, but it very lately reacts upon the price jump. So there are huge discrepancies here before actually your curve starts resembling the current prices again. So there is a lag here. Whereas if alpha is close to 0, then you obtain a smoothing curve, which is much more closely following the original one, but then you basically lose this desired effect of smoothing. So the closer alpha to 0, the less pronounced smoothing effect you get. So the design of this EMA is obviously not an all-dancing, all-singing solution for all cases. Uh, Apart from EMAs, there are more sophisticated, much more sophisticated filters, digital signal filters, which try to obtain good smoothing while at the same time providing a response to sudden price movements like what I have depicted here. But still, EMA remains very, very popular. So the question is, the typical operation we would like to carry out is EMA on our 1 terabyte or 10 terabyte of data per day, various EMAs. So then the question is, do you think that, let's say, Hadoop would be able to do this exponential moving average efficiently? I don't think so. Um, First of all, you may try to decompose this operation. You may try to think of how, let's say, map reduce and so on techniques would work in this case, but EMA, after all, is pretty much sequential. You really need your previous state in order to compute the new state. So, in fact, we need a very fast implementation of certain mathematical operations on your database. In this case, being implemented inside the database by embedded processing language. Whereas, well, very similar to how the language of stored procedures can be embedded in any SQL type database. For example, it does exist, as you know, it does exist for Oracle, it does exist for Postgres, and so on. So for time series database, we need a special language of stored procedures, which would allow you to implement typical operations such as, for example, computing moving averages and possibly some others, computing bands, min, max, and so on, inside the database without the external read operations, because obviously these read operations, especially in the distributed environment, in the client-server environment, would be tremendously insufficient. So that's a very important requirement, but it is also important not to overuse it. I think in your relational database, architecture discussion, you probably also discussed I would say conflicting and sometimes controversial points of whether a certain functionality is to be implemented in stored embedded procedures provided by your database technologies, or it is to be implemented outside of your database. We're finishing soon, but I would like to hear from you. Actually, have you been considering in the normal classical relational database technologies such design decisions using stored procedures or using the business logic outside of your database, and whether you are weighing pros and cons of both design decisions. Have you been doing something like that? It is a very important point. um, because you may gain extra efficiency by using stored procedures, but you would at the same time sacrifice portability, and it would be extremely difficult to migrate to a different type of database technology if a significant part of your business logic is implemented inside of your database in the language of stored procedures. As a typical example, many years ago, say Microsoft database server was extremely popular. Then with the decline of Microsoft platform altogether, migration was undertaken for many of them to Oracle, maybe Postgres, maybe other Unix hosted database solutions. And the software architectures significantly based on stored technologies were extremely difficult to port. Whereas the technologies implemented outside, the business logic implemented outside the databases, for example, if it was generic and portable Java-based implementation or something similar, was much easier to port and to manage the life cycle of the software. Same for time series databases, which we are going to discuss in very detail next time. Unfortunately, it seems that I will need to stop at this point. I promised to consider a mathematical example of using a time series database to model the epidemic outbreak, but we apparently have no time for that. And we'll do it next time together with constructive examples of how we do it in a database solution, in time series database solution, which is probably the leader nowadays from the point of view of both actually efficiency and functionality available, which is called KDB plus Q. But that is going to be the subject of our next discussion. For the moment, thank you for your attention. Any questions? If no questions, then we're stopping now. Thank you.